Section 4.6 is on performing operations with complex numbers. And our goal today is to perform operations with complex numbers. When we talk about complex numbers, we're talking about the imaginary unit, and that is I. So when we look at this, I, which stands for our imaginary unit, equals the square root of -1. So if we square both of those, we know that I squared equals -1. So essentially, that is what we're looking at in most of this section today. We're going to perform operations, and we need to make sure that we know that the square root of -1 equals I. And then if we ever get an I squared, that's going to equal -1. So the square root of a negative number says if r is a positive real number, then the square root of -r is I times the square root of r. So if we have the square root of -2, again, just like we did yesterday in the assignment, we're going to pull out any factors that we know. Well, we're always going to take the -1 out. And then it's -1 times 2. Now the square root of -1 is I, so it's I times the square root of 2. And then by property 1, it says it also follows that I times the square root of r squared equals -r. Well, if we look at that, we'll take the same type of problem. We'll say I times, and we'll go the square root of 2, and then we square it. Well, we're going to square everything here. So that means I have to go I squared times the square root of 2 squared. Like we set up above, I squared equals -1, and the square root of 2 squared is 2. So this is going to be -2. So what we're going to use that for is like problems in example 1. We're going to solve these. So if we solve this quadratic equation, again, we're going to do it using the exact same method we did yesterday, solving by square roots. Notice there's no x term in here, so we're going to solve that. So we're going to subtract 18 from both sides. We have 2x squared equals -90. Then we're going to divide by 2. So we have x squared equals -45. Well, just like we did yesterday, again, now we have to take the square root of both sides. So if we take the square root of both sides, we'll move this up here. We're going to get x equals, now again, plus or minus, and the square root of -45. So now we have to check, does this simplify? Again, using the two rules. First, is there any factors of 45 that have a perfect square? And the answer is yes. However, the first thing we're always going to do, if we see that that is negative, I'm going to pull that -1 out. So I have the square root of -1, and then our factors of 45 are 45 and 1. Neither of them are perfect squares. I mean, 1 is, but other than 1. But we do see that 9 is a perfect square. So we're going to take out 9. It's 9 times 5. So now we simplify this, and it's plus or minus. Square root of 9 is 3. Square root of -1 is I. And then we have the square root of 5 left. So let's go down to the guided practice where we'll have you try a couple of these. Let's look at question, let's do number 1 and number 3. And let's also go with number 6. So you can go ahead and pause the video and hit play when you're ready. And there are the answers to questions 1, 3, and 6. Notice every time you take the square root, you have to have the plus or minus. Anytime we have the square root of a negative number, we're going to pull that negative out. And it's going to become an imaginary number. The next thing we're going to talk about are complex numbers. And that's a number a plus bi, where a and b are real numbers and I is the imaginary unit. The imaginary number is a complex number in this form, a plus bi. So you're always going to write it like 2 plus 5i. The I is always going to come at the end, just like when we write the variable in there as well. So it's going to be, the I is always going to be at the end. So the sum and difference of complex numbers. And these are super, super easy. We're just going to do them just like we would do adding and subtracting fractions. Or not fractions, but variables. To add or subtract two complex numbers, add or subtract the real parts and their imaginary parts separately. So the sum of a complex number, if we look here, it's a plus bi plus c plus di. We're going to add the a plus the c. Those are the real parts. Then we're going to add the imaginary parts, the b plus the d, and that gives us the imaginary part. That's it. Same thing is going to be true down here for the difference. However, we do have to notice that this difference, if you wanted to write it, it would be a plus bi minus c minus di. So we have to use the distributive property there. So this is going to really be a minus c and then bi minus bd. Subtract those. So when we do these, again, add like terms. 12 plus negative 8, that's 4. Negative 11, negative 11i plus 3i is negative 8i. There's your answer. The next one, again, I would always switch this into, get rid of that negative sign in between and do the distributive property. So that way we're doing it exactly like we did part A now. And so we add our like terms, 15 minus 24, which would be negative 9. And then negative 9a plus 9a is 0. They're gone, so we get negative 9. And in C, we're going to do the distributive property. So it's going to be 35 minus 13 minus 4i plus I. And then again, just add your like terms. 35 minus 13 is 23 minus 3i. There you go. So quickly go ahead and do questions 7, 8, and 9 in the guided practice, and then you can hit play when you are ready. There are the answers to guided practice 7, 8, 9. We're going to skip example 3, and we're going to jump right down to example 4, which is multiplying. Same thing is going to be true here. In example A, we're going to use the distributive property. So if we do that, we're going to get negative 5i times 8, which is negative 40i, and then negative 5i times negative 9, which is positive 45i squared. So then we have to check, is this simplified? And the answer is no. You can never, ever have an I squared term. Because if we remember talking in the beginning of this section, I squared always equals negative 1. So we're going to go negative 40i plus 45 times negative 1. Well, that's just negative 45 minus 40i. And notice I switched it to put it in that order because we always want our imaginary part at the end. So this complex answer, or complex number, has an answer of negative 45 minus 40i. Well, and the same thing is true for B. You have a binomial, so we're going to FOIL them. So that's going to give us negative 32 for the first, the outsides, plus 56i, the insides, minus, plus 8i, and then the last is this negative 14i squared. So again, we're going to add our like terms, and we're going to end up with negative 32 plus 64i minus 14i squared. Once again, we're going to notice here we have an I squared. We can't have that. So it's going to be negative 32 plus 64i times negative 14 times negative 1. Well, that's going to be 14. And now notice we're going to have these two terms are like terms. So we're going to have negative 32 plus 14 So we're going to add those two together and then put our plus 64 at the end. So negative 32 plus 14 is negative 18. And then we're going to have our plus 64i. And there's your answer. So again, we're going to do those problems just like we did regular multiplication, only when we are done with that, we have to check if there is any I squared terms. That's the only difference between this and what we've done before. The next thing that we are going to talk about today is something called the complex conjugate. And two complex numbers of the form a plus bi and a minus bi. This is just like the radicals we did the other day when we talked about their conjugates. So we're going to write this in standard form. Now, just like we could not have a radical in the denominator, we can never have an imaginary number in the denominator. So what we're going to do is we're going to go about this the same way that we did the other day. We're going to multiply by the conjugate. Now notice, it's going to be the opposite sign of what we have as our denominator. And the reason being, if we FOIL these, and the outside terms and the inside terms are going to cancel out. So again, we're going to go ahead and FOIL both our numerator and our denominator. So 3 times 5 is 15, plus 3i, plus 20i, plus 4i squared. That's what we get if we FOIL the numerator. The denominator, 5 times 5 is 25, plus 5i, minus 5i, minus I squared. So let's go ahead and add our like terms up. We're going to end up with 15 plus 23i plus, oh, forgot my I, 23i. Now remember, I'm going to replace that I squared with a negative 1. We're going to do the same thing in the bottom. I have 25. Well, and see, notice here, the 5i and the negative 5i, they cancel out. They're gone. And now I have a minus negative 1. So we simplify this. In the numerator, we have 15 minus 4, which is going to be 11, plus 23i. In the denominator, we're going to have 26. So here's what we have. Now, we always want to write our imaginary numbers in a form that looks like this, a plus bi. So when we get to this, we are going to end up writing this as 1126 plus 2326i. So we're just breaking up that fraction. This way we have it as the real part plus the imaginary part, which gives us this complex number. So let's look at the guided practice problems. And let's do 11, 12, and 14. So go ahead and pause the video, and you can hit play when you are ready. There are the answers for the guided practice questions 11, 12, and 13. All right, the complex plane is a coordinate plane in which each point AB represents a complex number a plus bi. The horizontal axis is the real one. The vertical axis is the imaginary one. So these are going to be as easy as graphing regular ordered pairs. So 4 is the x-axis, essentially. So we're going to go over to 4, which is right there. And then up to here. So here is the point 4 plus 2i. This one, x go to left 1 and up to 3. That is negative 1 plus 3i. That one. We go right or left, nothing, and down 4. So here is the point negative 4i. And then the last one, 2 minus 2i. So we go 2 minus 2i, and there is that one. So that's all you have to do to graph numbers on a coordinate plane, on the complex numbers. And then the last thing we're going to do today is we're going to talk about the absolute value of a complex number. So the absolute value of a complex number, z equals a plus bi, is denoted by the absolute value. It's a non-negative real number defined such that a squared plus b squared, the square root of all of that. So that's the distance between z and the origin in the coordinate plane. And so that's how we find the distance between whatever the point is and the origin. So essentially, we're using the Pythagorean theorem for this. So if we look at example 7, we want to write or find the absolute value of 5 minus 12i and 17i. So essentially, this is two separate problems. We want to find the distance from this one to the origin. So if we write this, z equals 5 minus 12i. Well, the absolute value of z is going to equal, you're going to take your real part squared, okay, so the square root of 5 squared plus the square root of negative 12 squared. We're going to figure out what that is. So here, 5 squared is 25. 12 squared is 144. 25 plus 144 is 169. So we have the square root of 169. And the square root of 169 is 13. So the distance is going to be 13 units. So the point 5 minus 12i is 13 units from the origin. Now we're going to do the same thing with this one, with 17i. Well, we could write this as 0 plus 17i. Well, knowing what you know about graphing this, that means I go over 0 and up 17. So what should the distance be? Well, it's 17 units away. Well, let's check to make sure that that's what we end up with. So the square root of, we're going to go a is 0 squared plus b is 17, so 17 squared. So when we do this, we're going to take 0 squared, which is 0, and we're going to take 17 squared, and 17 squared is 289. And so that equals the square root of 289. Well, the square root of 289 is 17. And so our answer for that one is 17. All right, so quickly, go ahead and do questions 15, 16, 17, and 18. Go ahead and plot all of those. It says then find the absolute value of each complex number. I would just find, you don't have to do them all. Let's do just number 16. Find the absolute value of just number 16. But go ahead and plot the rest of those and hit pause when you are ready. Or hit play when you're ready. And here are your answers for 15, 16, 17, and 18. Notice when we found the distance of the point 3 minus 4i from the origin on the complex plane, we get the answer of 5. Now in these 3 problems that we've done so far, all of these have ended up being perfect squares. So like we had the square root of 25. That's not always going to be the case. If we do question 17, we'd find that you didn't get that. You'd get an answer of the square root of 29. So it doesn't always come out to be a perfect square, but that's how we would do those. So again, today we're talking about solving quadratic equations. Exact same as we did in the last lesson in section 4.5. The only difference is today we're using imaginary numbers. Now remember, or complex numbers too, but the imaginary number comes when we get the square root of a negative number. So the square root of -1 is I, and I squared equals -1. Those two things should probably make sure they get on your note card. So again, the square root of -1 is I, and I squared equals -1.